Welcome. So we're going to be looking at some contour integrals in this video. Roughly speaking, I am following a section from Complex Variables 2nd edition by Stephen D. Fisher, which is a great book. Let's get to it. So first of all, integrals of rational functions. When we look at a polynomial, say a n z to the n, and so forth and so on down to a0, if we divide that by z to the n, we get a to the n plus a to the n minus 1 over z plus da da plus a0 over z to the n. And if you think about the limit as the modulus goes to infinity of that expression, it's fairly clear that everything there dies except for the, leading coefficient, right? So the limit of the quotient of p of z over z to the n, the absolute value, the modulus of that, right, is the modulus of the leading coefficient. And so that means that this sequence of real numbers, right, is converging to that real number. So if you have a bound below the limit and a bound above the limit, then certainly you can, expect that the values of p to the z over z to the n are going to be between the lower and upper bound to the limit as you get closer and closer to infinity, right? Anyway, this is a reasonable bound given that limit. And that's really all you need, because for z sufficiently large, you can have, you get 1/2 the leading coefficient r to the n less than the modulus of the polynomial less than 2 times the leading coefficient of the polynomial. So when we have the polynomial in a denominator, we need that one. When we have the polynomial in a numerator, we need that one in order to implement the ML theorem. All right, so in particular here, the my stopwatch is off here. Anyway, so this gives us the theorem, which I proved in class using a slightly more sketchy argument. Well, it was really an incomplete argument when I did it in class this semester, but anyway. So if we have p and q polynomials real valued on the real axis for which the degree of q is at least 2 larger than the degree of p, right, and the numerator is degree 2 less than the denominator, then as long as the denominator is not 0 on the real axis, we can calculate the integral from minus infinity to infinity p of x over q of x by just 2 pi I times the sum of the residues, which all the singularities which fit in the upper half plane, right? And so the argument is familiar, I think, if you've been paying attention lately. And it's just this, we basically look at this half circle contour, and we assume that the degree of the denominator is at least, the degree of the numerator plus 2. And the boundary of the region is the line segment from minus r to r and the upper half circle CR, right? And all the singularities that fit in there are just the ones with positive imaginary part, because any singularities below the real axis are not included in that region, right? And so the residue theorem gives us that the integral over the boundary is 2 pi I times the sum of the residues. But on the other hand, the boundary is the integral from minus r to r, and the integral is over c sub r. But the thing is, the integral over the half circle, we can bound using the proposition right there, right? So the modulus of p of z over q of z is the modulus of p of z over the modulus of q of z, which is less than or equal to twice the leading coefficient of p times r to the n, or 1/2 the leading coefficient of q times r to the m. Right? So I'm using a's for the coefficients of p and b's for the coefficients of q here. And anyway, so that gives you an m for the ML theorem, and then the L is pi r, since the length of that circle is pi r, half circle rather. And so you get 4an over bm over 1 over r to the m minus n plus 1. And we're assuming that m minus n is greater than or equal to 2, which means that this is at least 1, which means it goes to 0 as r goes to infinity. And the theorem follows. So mostly I'm just presenting, we already did this, right, this semester, but my point to you is that this argument up here is pretty much complete and a nice way to see why this has to be why we get these bounds for r sufficiently large. All right, anyway, let's put this into practice then. So using that theorem on example 1, I'm going to integrate x squared dx over 1 plus x squared times 4 plus x squared. So our p of z is z squared, our q of z is that. Notice the degree of the denominator is 2 larger than the degree of numerator, so we've satisfied that needed condition. And what are the residues? Well, the residues that fit are, well, you have plus or minus I and plus or minus 2i as places where the denominator is 0, right? But in the upper half plane, we just have to look at I and 2i. I think I'm using rule, I believe this is rule 3, right? Evaluate the numerator, divide by the derivative of the denominator, right? And go through the details here, and I get this and I get that, which simplify to I over 6 and minus I over 3. And these are the only singularities in the upper half plane, therefore the integral of that is 2 pi I times the sum of the residues, which works out in this case to pi over 3. So, listen, I know working through those details takes more time. I should know. I just spent like 4 hours putting together what I'm about to show you in 40 minutes, okay? So let's go on. Some of these examples took much longer than others. I'll tell you when I get there. All right, so come on, paper, behave. So next up, integral from minus infinity to infinity of dx over 1 plus x squared squared. So again, applying the theorem, we need 2 pi I over the residue at I. See, because the only 0 to deal with here, the singular points for this are plus or minus I, but only plus I is in the upper half plane. So using the theorem on page 1, I just get 2 pi I times that. Now the residue of this works out to 1 over 4i, as I'll show you shortly. So the answer is pi over 2. So let's see why that's true. Now this one here is a double pole, right? Because 1 over z squared plus z squared squared, 1 plus z squared squared is z plus I times z minus I squared, which is 1 over z plus I squared times z minus I squared. So evidently, from this I see that z equals to I is a double pole. And so I need to use the theorem for calculating the residue at a double pole, which is this. We differentiate the function we're dealing with multiplied by z minus I squared, and then we differentiate that with respect to z. And I write it as the limit as z goes to I, but you could just as well say evaluate this at z equals to I. Same song and dance. So basically the z minus I squared factors cancel, and you're just left with 1 over z plus I squared differentiated, which... Uh-oh. This video may come to a premature end if I have to go cook burgers. Well, anyway, we'll find out. Let's keep going. So differentiating that gives me minus 2 over z plus I cubed. And then I evaluate that at z equals to I. All right. And that gives me 1 over 4i. So that's what put up there and give us the pi over 2, right? So again, this is the rule for calculating the residue of a double pole. All right. So, and I feel bad. We at no point in this lecture today am I going to go back to like the straight up calculate the Lorentz series method of calculating the residue. I'll be using the rules pretty much at every step here. But you should remember there are things we had before the rules which still can sometimes come into play, just not in the examples I have for you in this document, unfortunately. Okay, so next up, this example, it took me an inordinate amount of time to work out. Because there was an answer in the back of the book which I still don't understand. So whatever, but anyway. Well, I mean, I understand that the answer in the back of the book is the same as my answer, okay? But, so here it is. Integral from minus infinity to infinity of x to the 4th dx over 1 plus x to the 8th. So we do 2 pi I times the sum of the residues that are in the upper half plane. So what's going to be a singularity here? It's going to be something that 1 plus z to the 8th is 0, right? Well, that would mean that z to the 8th is equal to minus 1, which would mean that z is an 8th root of minus 1. But the principal 8th root of minus 1 is e to the pi I over 8, right? Because remember, minus 1 is e to the pi I, and so you just divide by 8 to get the principal root. And then there are other three, so multiplying by the 8th, the 8th root of unity, which is, as it happens, e to the pi I over 4. And so multiplying that, then that, then that, leaves me with these four, these are the four singularities of the function which land in the upper half plane at pi over 8, 3 pi over 8, 5 pi over 8, and finally 7 pi over 8. There's 4 of them. 4 of the 8 total singularities of this function land in that half-circle contour that Theorem 1 considers. And it turns out that the residues add up to this. And so the answer is pi over 2 times the sine of 3 pi over 8 minus pi over 8, which is, by the way, about 0.8501. Now here's how that goes. So in each case, the residue can be calculated from rule 3. So I take the numerator, I plug in zj, differentiate the denominator, it gets 8zj to the 7th, which then simplifies to 1 over 8zj to the 3rd. All right, and that's true for every 8th root of minus 1. We're only interested in the ones in the upper half plane, though, of course. And so here they are. Here they are. So I plug in that into this formula, I get this. I plug in that into this formula, I get that. But here's a trick. This is e to the 9 pi I over 8. So that's e to the 8 pi I over 8 times e to the I pi over 8. But e to the 8 pi I over 8 is e to the pi I, which is minus 1, so I get that. And here I've subtracted 16 pi I over 8, which is 2 pi. Right? That we can do that because the imaginary exponential is 2 pi periodic. So this is actually 1 over 8 e to the minus pi I over 8. And this guy, I subtracted, let's see here, what did I do? Oh, yowzers. Well, there's a minus, but anyway, this simplifies to that. And, okay, fine. So to get the minus, you could think of, curses. So if I split off 8 of this, I get e to the 21 minus 8 is what? 13? So I get a minus e to the 13 pi I over 8 downstairs, and then I subtracted 16 as I can do because that's 16 pi over 8 is 2 pi, so by the 2 pi periodicity I get that. Anyway, this simplifies to that, and then when you add all of these things together, tilt your head and squint, you can turn these into sines of 3 pi over 8 and pi over 8, and you get that. Now, the answer in the back of the book. All right, because this is, again, this is from Fisher's book here, where I got this. It's all Fisher's fault. He did this to me. Right here, this is the problem I was working. Number 1, integral of x to the 4th over 1 plus x to the 8th dx, right? Section 2.6, number 1. The answer in the back of the book. I did recommend this book to you guys, did I not? I believe I did. It costs like tens of dollars, you know. So 2.6, number 1. Where'd you go? Come on. Show yourself. 2.6, number, well, oh, here we go. 2.6, number 1. Answer in the back of the book. See that right there? pi over 4 divided by the sine of 3 pi over 8. I've plugged this into Wolfram Alpha. It is 0.8501. This is the same answer as that. So it took me, I don't know, more time than I'd like to admit to finally come to terms with the reality that I already had the right answer, and you know. Anyway, let us move on, as that problem has already taken too much of my life. Example 4. Here we go. Now we're going to look at integrals along the real axis involving trig functions, all right? So here I face the integral from minus infinity to infinity of cosine x over x squared plus beta squared, where beta is a real positive constant. So in order to get my pause on that one, I look at the corresponding complex function e to the iz over z squared plus beta squared, because you see that simplifies to e to the ix over x squared plus beta squared, which is, by the way, cosine x plus I sine x over x squared plus beta squared for x real. Which means that if I integrate this thing, it's going to give me insight into the integral of cosine x over x squared plus beta squared, and also sine x over x squared plus beta squared, although it turns out that that's not interesting in this case, because it's an odd function, and it integrates to 0. So again, we take the half disk, like so, and we notice that the only singularities that fall within the half disk are I beta, in this case. So we get integral over the boundaries, integral from minus r to r, plus the integral over the half circle, 2 pi I residue of my function at I beta. All right, and then I just calculate it. So here's the calculation. Let me scooch this up a bit here. So the integral for the half circle, we have z is the r e to the I theta, which is, by the way, cosine theta plus ir sine theta. So when we plug that into e to the iz, we get e to the ir cosine theta minus r sine theta. The imaginary times the real thing has modulus 1. That dies in the calculation, and we're just left with e to the minus r sine theta. But the thing is, as long as r is greater than beta, noticing that, sine theta is between 0 and 1 for theta going from 0 to pi, as we would want it to on this upper half circle. So e to the minus r sine theta is at most e to the 0, which is 1, by the way. So there you go. We can replace this with 1. We replace the denominator with r squared minus beta squared, provided that the modulus of z, which is equal to r, is greater than beta. So we get that. And then the ML theorem does the rest for us, of course, because the limit as r goes to infinity of this is less than or equal to the limit as r goes to infinity of pi r over r squared minus beta squared, which is 0. So in what's perhaps becoming a familiar story, that piece dies, and we can calculate the residue by, in this case, rule 4. Is it rule 4? Oh, I think that's rule 3. It's rule 3, if I remember right. Because I evaluate the numerator at the residue, and I differentiate the denominator, and then evaluate that derivative as 2z is 2I beta. And so, but on the other hand, notice that the integral from minus r to r here is the integral from minus r to r f of x dx, right? And as r goes to infinity, we get the integral from minus infinity to infinity of cosine plus I sine x over that x squared plus beta squared is equal to 2 pi I times the residue, which, by the way, simplifies to the i's cancel, the 2's cancel. We're left with a pi e to the minus beta over beta. And what's going from here to here, what I'm doing is that the integral of sine x over x squared plus beta squared, that's 0, because sine x over x squared plus beta squared is an odd function, and an odd function symmetrically integrated about the origin integrates to 0. To be more fussy here, what I've really calculated is the principal value of this integral. And, okay, fine, there's probably some more song and dance that needs to be given here in order to be sure that the integral exists and equal to its principal value. But nevertheless, I will omit the PV here. I will bring the principal value back in a future page. But anyway, there it is. Another example. So this is very similar to the example we just did. I just introduced a parameter here just to make it a little bit more fun. Really, we could have just done this example and skipped the other one, but I have no regrets. So integral from minus infinity to infinity, cosine beta x over x squared plus alpha squared. Here, alpha and beta are simply positive constants, real constants, of course. And so what we have is one singularity to calculate the residue at, namely I alpha, and I calculate that by rule 3, I believe, and that gives me e to the minus beta alpha over 2I alpha. Once more, the modulus of the integrand is bounded by, as it happens, 1 over r squared minus alpha squared on the half circle, which then the ML theorem gives us 0 in the limit. And then the integral of minus r to r of e to the I beta x over x squared plus alpha squared gives me two pieces. It gives me the cosine and the sine. But the sine piece is an odd function, so that integrates to 0. That's the piece we're interested in. And so, by the residue theorem, and then taking the limit as r goes to infinity, we get the integral of cosine beta x dx over x squared plus alpha squared is equal to 2 pi I times that residue, which simplifies to pi e to the minus beta alpha over alpha. So, there we go. You know, it's funny how these examples work out better when I work them out before I tell them to you. And also before I try to do anything. Well, I'm not trying to work out anything on the board right now, am I? So it's all going better. Anyway, so listen, these problems are complicated. It's so easy to make a mistake somewhere in the weeds here, and you know, it just takes one mistake and everything else just. But there's something else neat to do here. Now that we have this formula, which has a dependence on parameter beta and alpha, Fisher points out that you could do this snazzy differentiating under the integral trick. He just says it's an unjustified formal calculation, I believe, which is accurate for this lecture. But you can prove that you can commute the order of partial differentiation and integration given a particular condition on the integrand. I believe uniform continuity will do it for you, and there has to be some other condition at infinity. I forget exactly, but anyway, in an advanced calculus class that's offered nowhere, you can prove that. And so we get that differentiating this is equal to the derivative of that, but you bring the derivative inside, and so differentiating that, of course, gives us, with respect to beta, gives us a minus alpha pi e to the minus beta alpha, so the alphas cancel and you're left with minus pi e to the minus beta alpha. Differentiating this gives you a minus sine beta x times, see, the thing is the partial derivative with respect to beta of beta x, right? It's equal to x. So that's where that x comes from. And then you got a minus from the cosine integral, you got a minus from that, derivative, and minus from that derivative as well, so you get the minuses cancel, and you're left with the star formula, which is pretty awesome. On the other hand, you could differentiate the star formula with respect to alpha and get the integral of x sine beta x over x squared plus alpha squared is equal to pi e to the minus beta alpha beta over 2 alpha, which is also pretty snazzy. And you could also take beta equals to 1 and let alpha go to 0, and that will derive from this that the integral of sine x dx over x from minus infinity to infinity is pi. Now this is a little bit more sketchy because there's a divergence at 0 which we did not face in the derivation of this thing, right? So this is a little bit out of bounds because like the thing you're, well, I don't know. I'm this little, but anyway, we'll derive this through a more legit argument as we go on here. So let's go on. So differentiating under the integral and finding a result that depends on a parameter, and then exploiting that parametric dependence is something we don't talk nearly enough about in the math major. That's essentially what's known as Feynman's trick. Anyway, so Jordan's lemma is the next step here. It's a little bit more nuanced than the estimates we've been using so far. It's much closer to being on the bubble of failing. The things we've been doing so far have been a little bit greedy, I would say. So the modulus of the integral over the upper half circle of e to the I z dz is less than pi. That's what the Jordan's lemma says. So the proof is just a calculation, pretty much. Here it is. So this is equal to that. I'm just putting in this z equals r e to the I theta, and then that simplifies to r e to the minus r sine theta. It's essentially the calculation I did in a previous example. And then by symmetry, we can just double the integral from 0 to pi over 2, you know. And then there's a sneaky estimate you can make. See, because sine theta is bigger than 2 theta over pi, if you're going from 0 to pi over 2, like that. So I can replace the r sine theta with the much easier to integrate theta over 2r theta over pi, like that. Straight up do the integral, evaluate it, and therefore we get the integral of e to the I z dz over the half circle is less than or equal to 2r times pi over 2r times 1 minus e to the minus r, which gives us pi. This first term simplifies to pi minus something positive, so just replace it with pi. There you go, Jordan's lemma. Let's put it into practice. Here's an example. So, integral of x sine x over x squared plus 1, I look at z e to the I z over z squared plus 1. First of all, notice for the upper half circle, we have the modulus of this is less than or equal to, the z gives me an r, z squared plus 1 gives me an r squared minus 1 through the triangle inequality. And then of course I still have to deal with the modulus of e to the I z dz, but that's less than pi. By Jordan's lemma, we get pi r over r squared minus 1. Now that goes to 0 as r goes to infinity, so hooray! And then we're looking again at the half circle contour, and so the only residues that are of interest are the ones in the upper half plane, namely I for this one. And that by rule, I would say 3 again. I get I e to the I squared over 2i, which gives me 1/2 e to the minus 1. So integral over the boundary of the half circle, I get the real axis integral, that's the half circle integral, that's equal to 2 pi I times the residue, which in this case is pi I over e. But remember, the function that we're integrating is actually x cosine over x squared plus 1 plus I x sine x over x squared plus 1, which, because notice here that the x cosine x over x squared plus 1 is actually odd in this case. If you replace x with minus x, you get minus what you started with. In contrast, this is even, so it's okay. It doesn't automatically integrate to 0. Integral from minus r to r of f of x dx then simplifies to just I x sine x dx over x squared plus 1. And then if we let r go to infinity, we get I times that integral equals I times pi over e, which then dividing the i's gives us this. Hooray! So there's an application of Jordan's lemma. Notice that we're walking a finer line here. Now we've got the degree of the denominator is only 1 bigger than the degree of the numerator times a sign. Yeah. The examples up till now had like the degree of the denominator was at like order 2 more than the numerator. Here's another one that walks that line. In other words, the numerator has degree 1 more, just degree 1 less than the denominator, and there's a sign. So here, x cubed upstairs, x to the 4th downstairs, but the sign upstairs helps out. So as it turns out, we look at z cubed e to the I z over z to the 4th plus 1. Singularities for this guy are 4th roots of minus 1. There's two of those in the upper half plane that concern us, so we calculate the residue at those two things, like so and like so. See, these are the two singularities I have to deal with in the half circle contour. And so this at e to the pi I over 4, I think I use rule, well, this is just getting boring. It's rule 3 again. All right, rule 3 again, and the details are here and here, and it works out to this and that. And notice that you gotta be careful to sort through these things. Like I times I is -1. The thing is sine of pi over 4 is 1 over root 2. So there's like lots of 1 over root 2's here. You end up with e to the -1 over root 2, and you got your cosine of 1 over root 2, you got your sine of 1 over root 2. Same song and dance down here, but there's a minus on the imaginary parts. It's almost exactly the same, right? Except that there's this, why is there no fourth there? No momento. I feel like I've lost my 4. Oopsie doopsies. 1/4. 1/4. 1/4. There we go. I bet I recovered the 1/4 down below. So apply the ML theorem and Jordan's lemma over the half circle, and we get that the half circle goes to 0, and again, since odd functions integrate to 0, this just leaves us the sine piece. And so then applying the residue theorem, we get I times the integral of the x cubed sine over x to the 4th plus 1 plus the integral of the piece which we know goes to 0 is equal to 2 pi I times the sum of the residues. That and that cancel, and it just leaves us with, and then you notice there's an I here, but there's also an I here, so those I's cancel, and that leaves us with integral from -infinity to infinity. And the limit as r goes to infinity, of course, right? X cubed sine of x dx over x to the 4th plus 1 is equal to pi e to the -1/2, and then I get, see, I've got a half from this one, and I've got another half from this one. 1/2 plus 1/2 is 1, so I just get cosine 1 over root 2. All right, let us go. Next up, indented contour integrals. So here we look at things of the form like this, integral of sine x over x dx. So we saw that that was pi over, I think it was pi. Yeah, it was pi before, we found from the sneaky trick. But now we'll use an indented contour to calculate it more carefully. So if e to the iz over z, right, that gives us f of x is cosine x plus I sine x for real z rather, is equal to x. And if we look at, this is the indented contour, so we just take a little indentation around 0, right? 0 is a trouble spot. We can't just run through 0 because the function's not defined there, you know? So what we do is we just put a little loop around it, like that, a half loop actually. And so, you know, dr comma epsilon would be this entire, you know, half annulus, I guess. And so you've got the circle, counterclockwise half circle CR, and the counterclockwise half circle C epsilon. So I put minus C epsilon here because it's going the wrong direction. It's going clockwise. But just to stay out of trouble, I'm working with C epsilon being the counterclockwise one because the fractional residue theorem we proved was for a counterclockwise one, right? So here's the deal. By Jordan's lemma, we can integrate e to the iz over z is less, so that's less than or equal to 1 over r, integral of e to the iz dz modulus, that's less than pi, so we get pi over r. Of course that goes to 0 as, you know, r goes to infinity. On the other hand, the integral around the c epsilon, right, the little indentation, is that indentation shrinks to 0, we pick up a pi I, because the residue of e to the iz over z at 0 is just e to the 0 over 1, which is 1. So pi I is what we're going to pick up from that piece. So this function has no singularities inside the boundary of the dr epsilon region, and so the integral over the boundary of that region is 0. And if we allow epsilon to go to 0 from the right and r go to infinity, we find in this double limit all of that's equal to 0. But what that's giving us is the integral from minus infinity to infinity of cosine x plus I sine x over x from, these pieces here. And the r piece goes to 0. This other piece, I moved it to the other side to make it plus the epsilon, right? That gives us pi I. The integral of cosine x over x integrates to 0 because it's an odd function. Sine x over x is even, it survives, and then the i's cancel, and there you have it. Integral from minus infinity to infinity, sine x over x dx is equal to pi. You can compare that to page 5, where we derive this by a sneaky trick. So there's an indented contour for you. Here's one with a little bit more indentations. So here we calculate so now I'm finally doing my due diligence in talking about principal values. So what is a principal value? Principal value, PV means principal value. It means we approach the singularity symmetrically. Truth be told, I think almost everything I've calculated in this lecture is a principal value. Although I do think that because of calculus 2 I don't want to talk about, they all actually exist and are equal to the integrals. That's probably not true for this one, though. I think the principal value here exists, but I don't think technically that the corresponding improper integral actually exists. Okay, so because typically speaking, stuff like integral of 1 over x is not going to exist in a double-sided sense. Anyway, if the left and the right limiting processes are not connected, I don't think that exists. So, but if they are, then it does, and here's how. So, so this function will look at the complex function e to the iz over z times z minus 1 times z plus 1. We have to make an indentation at 0, 1 and minus 1, right, if we're going to use the half circle. And so the residues at the indentations are minus 1, e to the I over 2, e to the minus I over 2 as it happens. And I'm using minus r to r in quotes as a hack notation for this line segment, this line segment, this line segment, and that line segment all unioned, because I don't want to invent 4 names and write 4 integrals. And then, of course, minus the integral over the counterclockwise oriented epsilon 1, epsilon 2, and epsilon 3. That's equal to the integral over the boundary of d, I should say, of f of z dz, which is just 0 here because there is no singularity except for on the edge for this guy. So in the limit of the indentations shrinking to points, we get, by the fractional residue theorem, in each case here the fractional residue is a whole half circle, right? So we get, instead of 2 pi I, we get pi I, and then minus 1 plus this, which, after a moment's reminder of what cosine is I pi times cosine of 1 minus 1. Yay. And so this gives us that the principal value of the integral from minus infinity to infinity of sine of x over x times x squared minus 1 dx is in fact pi times cosine of 1 minus 1. Yay. Now we have arrived. Integrals at branch points. Okay. So I'll tell you what, we will, well, let me go on. I feel like I'm about to be called away to do burgers, but foolishly forge ahead. All right, so integral of 0 to infinity of log x over 1 plus x squared squared. So this is the one I tried in class last time, and it kind of, well, I didn't try this exactly, but I tried something like it, and it just blew up at me, because I forgot how to do it, and the way I was doing it was not helpful, as we saw. So here's how to do it. So if you have like log x over 1 plus x squared, what you want to do is look at log of alpha of z over z squared plus 1, where this is the branch of log alpha which has its branch cut on like the negative imaginary axis. So we'll put the angle jump down here. That way we can do this indented contour and have the log defined on the whole deal, right? And then the angle jumps down here. So in this way of doing it, we have log alpha of z, of course, is natural log of the modulus of z plus I arg alpha of z. Here, arg alpha of z is the angle taken from minus pi over 2 to 3 pi over 2. So like the angle 0 on this branch, on this part of the, from epsilon to r, but the angle's pi over here, okay? And so that's going to make us get a different formula for f on this piece versus that piece. And so in short, when we also, of course, as usual, we get the integral over the half circle is less than or equal to this estimate for these reasons up here. See, if you just make the r such that natural log r is larger than pi, then the biggest the angle could be, this arg alpha could be on the half circle would be pi, right? So if I replace arg alpha with pi, well, if I replace that pi with a larger log r, then I get this. So this modulus is greater than that, which gives me square root of 2 log r. So the point is, you got to do something to take care of the part of the modulus that comes from this. And so I just said, oh, suppose log r is larger than pi. That's a reasonable assumption. That just means that r is greater than e to the pi. So under that assumption, and the assumption that the modulus of z is larger than 1, which of course it will be if it's larger than e to the pi, which is like 9 or something. Wait a minute, no. 30? I don't know. Anyway, so we get this bound on the function. Root 2 log r over r squared minus 1 squared. So by ML theorem we get this, which then goes to 0 as r goes to infinity. Maybe you need to apply L'Hopital's rule, whatever, but it's clear that this goes to 0 by usual calculus 2 stuff. On the other hand, you can also argue that for the inner circle, we have the log of epsilon going to minus infinity. It's approximately minus. See, if epsilon is very, very small, then the log is very, very large and negative, which means that the natural log of epsilon plus I arg alpha is going to be less than minus 2 log epsilon. See, because certainly this here, and I probably need a minus. I probably should put a minus there. But definitely this is going to be dwarfed by another minus log epsilon. That's way bigger than any angle you can pick there. So we get this estimate, this bound for the modulus on the little indentation half loop. And so then again, by the ML theorem, in the limit epsilon goes to 0, this piece goes to 0. So that gives us the following. So I'm going to have to, well, we'll come back to the residue in a second here. The residue of the function at I ends up being 1/8 pi plus 2i. And so in the limit that the outer loop goes to infinity, the indentation shrinks to the point. We end up with this plus this plus this plus this is 2 pi I times the residue, which is minus pi over 2 times I pi squared over 4. And notice that the integral over the negative real axis picks up the I pi term, all right? Whereas the integral over the positive axis does not, because angle's 0 for the positive, angle's pi for the negative. So you pick up that extra piece here. I'll explain that more on the next page also. So anyway, if you take those limits, you notice that you got I feel like I might be missing a 2. Oh no, so I put together the log x's, this log x over x squared plus 1 squared and log x over x squared plus 1. I put these two together to give me the integral from minus infinity to log x over x squared plus 1 squared. And then the I pi term gave me this integral from minus infinity to 0. And then equating the real and imaginary parts of this gives me one thing. It gives me the integral from 0 to infinity of log x over x squared plus 1 squared is equal to minus pi over 4. Now, what I did there was I chopped the integral from minus infinity to infinity just to half of it, and so I divided this by the symmetry properties of the integrand. And I actually need to do that, otherwise this would have to have a absolute value of x, because for negative x I can't really. To be fussy, I should either put an absolute value here, or I should write minus x, yeah, because you can't take log of a negative value there. My bad. Anyway, so dividing this by 2, and like just instead of minus infinity to infinity, I do 0 to infinity, and that is why that would be half of what this is, which would be half of what that is, which is minus pi over 4. And the imaginary part, I've got a pi squared here, I've got a pi here, so I divide by pi and it gives you that. So anyway, all right. That one's a little tough. Now, some details I relegated to the next page. So just to emphasize why those are different, for arg alpha of z1, we get pi. Arg alpha of z2, we get 0. So log alpha of z1 is log of z1 plus I pi, whereas, my bad, modulus of z1, whereas log alpha of z2 is just the natural log of the modulus of z2. Now, specifically, that would be like, technically that would be natural log of like minus x plus I pi, and this would be just, natural log of x. So this would be z2 equal to x, and this would be, well, good grief, let me not say that. Let me not say that. That's not helpful. I'm thinking of x as being positive when I write minus x, but let me not do that. This is not productive. There we go. All right. Sorry about that. Moving along, and the residue. Well, the residue actually takes a little work. It's a double pole, so you got to do the derivative. You take the function, you multiply by z minus the singularity squared. That cancels out the piece which is singular in here, and it leaves you with the other part, which is log alpha z over z plus I squared. So the z minus I squared term cancels in there. And then you differentiate. I use the product rule personally, and then I evaluated I. I have to calculate the log alpha of I. That is the log of the modulus of I plus I times arg alpha of I. But remember, I is at pi over 2, so we get I pi over 2, which then gives me the thing we used on the last page. All right. Moving on. Example 11. We have the integral of x to the p, x to the power p, of 1 over, divided by 1 plus x squared, integrated from 0 to infinity. P being some real value between minus 1 and 1. So this time we'll use the logarithm, again, with the branch cut along the negative imaginary axis. So we'll have f of z is z to the p over 1 plus z squared, where in particular that complex power we're defining as exponential of p log alpha of z. That was how we defined the complex power function, right? And so along the real axis, we just have arg alpha of z is 0, so f of x is just x to the p over 1 plus x squared. But along the negative real axis, we get arg alpha of z is pi, and so when you simplify x to the p, you end up with minus x to the p over 1 plus x squared e to the I alpha p. And so, see, because if x is less than 0, then the modulus of x is minus x. That's why that's there, okay? Anyway, so same song and dance. Well, a little bit different. Here we have a residue at I, so that gives us I to the p over 2I. And then the integral over the half circle. Uh-oh. Ooh. Oh, looks like Isaac might have lost. I don't know. Tell me. Uh-oh. So then we have this bound for the half circle, we have that bound for the inner loop. Those both go to 0, and r goes to infinity, and epsilon going to 0. And that just leaves us with the integral from minus infinity to 0 of this piece here. Notice the e to the pi ip, because the arc alpha is pi there. And on the other hand, the other piece has the angle 0, so you just get the integral from 0 to infinity on that other piece. And then 2 pi I times the residue, which gives us pi I to the p. But if we make a change of variables, basically to change this integral from minus infinity to 0 to instead 0 to infinity, which is basically make a u equals minus x substitution, then this integral is that integral just times e to the pi ip. So you get 1 plus e to the pi ip times the integral you're interested in equals to that. And consequently, you get the integral is equal to that, which is equal to that, which multiplying the top and bottom by e to the minus pi I p over 2 gives you that, which by the way is pi over 2 cosine p over 2. So, yep. That's another example. And finally, last but not least, we have the keyhole contour integral. Here we go. And so for this one, I will, so we have to work x to the 1/3, we have to define using branch cut of a logarithm. This time we'll use the branch cut at the positive axis. And so then we use this, I call it a keyhole contour, but this doesn't look like a keyhole exactly, does it? But you remember the picture we drew in class, looks more like a keyhole. It's basically the same idea. The point is that this region has two singularities for our function, -2 plus or minus 2i. And the boundary, you've got your inner loop and your outer loop, and your L plus and your L minus. Along L plus, we get the log, the complex log just becoming the natural log of x. On the L minus, we get the complex log becoming the natural log of x plus 2 pi I. And so altogether, we have integral from L plus L minus the inner loop plus the outer loop is 2 pi I times the sum of the two residues. You calculate those residues. Well, first of all, a little bit more on L plus. On L plus, we can think of, we get basically f of z is essentially x to the 1/3 power over x squared plus 4x plus 8. On the other hand, on L minus, you get this phase factor from the logarithm. Having angle 2 pi, you end up with a 2 pi I over 3 because of the third root, and then x to the 1/3 over x squared plus 4x plus 8. So there's no x and minus x here because they're both really, really close to the positive axis. They just have different arguments when they're a little bit below versus a little bit above. And the integrals over the inner and the outer loop both go to 0. I'll let you see the details of that. The residue calculation, here it is. It's a little bit pesky. I basically have to calculate that 1/3 root of -2 plus 2i, which in polar form is the square root of 8 times e to the 3 pi I over 4. which then simplifies back down to the square root of 2 or 4i e to the pi I over 4. Likewise, the residue at the minus 2i term ends up with giving me a, square root of 2 e to the 5 pi I over 12 times over minus 4i. Again, it would take me about 20 careful minutes to calculate that. It'll take you that long too. There they are. Gotta be careful. So putting it all together, here it is. We have, as epsilon goes to 0, r goes to infinity, from the star back on page 13, we have 2 pi I over 3 times that integral plus that integral is 2 pi I times the sum of the residues, which, again, just flip the bounds. No u substitution here, just flip the bounds, and we get 1 minus 2 pi I over 3 times the integral is equal to that, which, through this straightforward simplification, leads you to the answer being pi root 2 over 2 times sine of pi over 12 sine of pi over 3. So, anyway, that's it for today, folks. Thanks, guys.